We're back with Chapter 7, and we're going to look at Section 7.3. This is quite a long section in the book, and there are quite a few steps to this. As you can see here, looking at the learning objectives, we want to list the steps to derive the energy equation here. We want to explain flow work and shaft work. This is a way of kind of separating out the work of pressure in the fluid, what we call flow work, from work that can be done on the fluid by a pump or by the fluid by a turbine. That's what we call shaft work. We're also going to define a couple of important concepts. Primarily, the head loss is a very important concept in fluid dynamics. And also the energy conversion factor, this alpha term that we talked about in the last video, just briefly, as something new that kind of shows up in the equation. And then we're going to kind of basically describe the physics of the energy equation and the meaning of the variables. And then I would say in later sections we're just going to briefly mention how we apply the energy equation at the end, and of course in subsequent sections we will work with the equation. So let's skip forward now all the way through to section 7.3 and get going. This is where we started, or kind of where we ended last time. I just wanted to make a point of where are we headed. And I wanted the point I made before is that the energy equation looks an awful lot like the Bernoulli equation. And as I mentioned, there are a couple of new concepts. Alpha is something called the kinetic energy factor, which is important. You can see over here that it's listed, and we'll look at this again in a minute, but that it has a value. Usually the value is just 1. But you can see that alpha can be 2 for fully developed laminar flow in a round pipe. And we will derive an equation for alpha that will let us derive this or calculate it if necessary, if we ever need to do that. But basically, it's related to the velocity and how the velocity is related to a uniform distribution of velocity. So we'll look at that in a minute. So alpha is new, and we're also using the average velocity, v bar, instead of v, because basically we're encapsulating the velocity inside this alpha parameter. We'll see that in a minute. The other thing that I want to draw your attention to is, of course, these major assumptions here that we are making. It's going to be steady state, so we're assuming that there will be no energy accumulation in the control volume, which should help us simplify the Reynolds transport theorem. Another key component is that the control volume only has one inlet and one outlet. And so that's a restriction on this particular formulation of the energy equation. But we could see, there are a lot of problems that we can solve with that. We can have a pump at one inlet and a turbine at the outlet, for instance. We can also have to assume constant density flow. That allows us to simplify the equation a bit. We're assuming that all the thermal energy terms, except for the head loss, can be neglected. We'll see how that comes out in the equations. And streamlines are straight and parallel, as they have been in most of what we've done already. And that temperature is constant across each section of the pipe. So let's move into the derivation, and I would encourage you to read carefully through the book. I'm going to just kind of hit the highlights here in this lecture. So the derivation starts by looking at the intensive property, little e. Remember from last time that little e is equal to the energy divided by the mass. And so if we attempt to write out all the different types of energy that we have, we have kinetic energy per mass, potential energy per mass, and then we have a U parameter, which we're using for just to kind of accumulate all the internal energy. This would be changes in things like the molecular motion, kind of things within the fluid itself. And you'll find that this term here is going to be represented by the head loss term, H sub L in the end. So we'll get there in a minute, and we'll kind of carry along these U's. So when we plug these in, we obviously E goes right here and here. We saw that last time. We also can write down expressions very easily for the kinetic energy per unit mass, because we know that the kinetic energy is 1/2 mv squared, and that over mass is just going to make this v squared over 2. And the potential energy is just mgz, where z is elevation, g is acceleration of gravity, and this divided by mass is just, whoops, running out of room there. That divided by mass is just gz. So we have simple expressions for both of these terms here, ek, e sub k, and e sub p. So what are they? They're the kinetic and potential energy per unit mass. So that's the first thing that we're going to do. We'll see when we start writing the equation down that we'll put in those values for ek and ep. There's a couple of simplifications that we need to make, or derivations that we need to do, and we'll see how these work out. And again, I encourage you to read carefully through the book, through section 7.3, to get the details of the derivation. So the first simplification is the separation of the work into what's called shaft and flow work. The flow work is associated with a pressure force. And we know that, if we have a pipe here and we have a control volume in it, we know that there are pressure forces on, a compressive pressure force on either end of the control volume. So this is really what we're getting at with the flow work. And you'll see in a minute that flow work turns out to depend on the pressure. So this is really, you can read more about this, but this is really what we're getting at. We're separating the work out into the work done by the actual flow, the pressure in the fluid, versus work that might be done by shaft. And shaft is any work not associated with a pressure force. And this is where we get pumps and turbines. So this is in the end, we're going to have a symbol here of WS that we're going to carry through the derivation. That'll be the shaft work, and in the end, this will be separated into pumps and turbines. And in fact, it'll be the head loss, or the pump head and the turbine head. So we just separate this out. We've got the shaft work here is going to be turbines, and the rate of work done by the turbine minus the rate of work done by the pumps. And notice the sign conventions. This will all kind of wash out when we write the final equation. What is flow work? It is defined as being this work that's done by the pressure forces. So we can see here that we've got pressure here. It gets written in this manner, and the entire rate of work is then the flow work plus the shaft work. And remember that this is turbines minus pumps. And these will come back in the end when we write the equation finally. So we're going to have to carry along this pressure term, and that's what's going to give us the pressure term that makes the energy equation look like the Bernoulli equation. So when we plug all this back in, you can see that we have we still are subtracting out. Maybe I should use the pointer here. We're still subtracting out the work, but this is only the shaft work now, and the flow work has been added over here into the control surface, right here. And so we have now added the EKs and the EPs, the energy per unit mass for kinetic and potential energy, and plus the internal energies per unit mass, U, to both the integral over the control volume and the control surfaces. And we have this additional term over here, which is the flow work that comes into play. The book also mentions that in thermodynamics, the term enthalpy is given by the pressure divided by density plus U. And so in this case, we just replace this term up here, U plus P over density, or rho, with H. I think this is not a great thing to do for this derivation because H is also used for head. So we're going to revert back here in a minute to using U and P, but this is kind of a dangerous thing. So I'll just kind of circle this in red as being something this is enthalpy in this case, not head. It's kind of an annoying thing here. But in any case, suffice it to say, we've got this equation here. I'm going to rely on this equation here going forward. And we're starting to see some things in here that make it look like Bernoulli's equation, pressure and altitude and velocity terms. We still need to deal with these U's, and we still need to deal with the shaft and this heat transfer. But that's all going to come out in the derivation. So the second simplification that we need to make is to introduce this idea of the kinetic energy correction factor. And this is going to we do this as a matter of convenience in engineering, and just to show you physically what's going on. At point 1 here, we might have some velocity profile that looks like this. And if you can see that the diameter of this pipe is a little bit less here, and the velocity profile changes. It still looks parabolic, but it changes shape a bit. It's a little bit steeper. And so we need a way of kind of tracking the kinetic energy. Obviously, we need to integrate, the velocity across this, the velocity squared actually. The kinetic energy across this control surface is going to be, 1/2 mv squared, and the velocity is varying from 0 at the walls to a max in the middle at both locations. So we need a convenient way to deal with kinetic energy going in and out of the flow, or in and out of the control surface. So we introduce a term called the kinetic energy correction factor, which is the actual kinetic energy per time that crosses a section, a control surface. That's what they mean by section. And that's going to be divided by the kinetic energy per time by assuming just a uniform velocity distribution. So all of a sudden, that's where our V bar comes in, is we basically use this alpha term to trick the equation so that we can use a uniform velocity, V bar, as long as we know what alpha is. So when we boil this all down, alpha becomes this value right here, 1 over the area, times the integral over the area of the true velocity profile. That would be the velocity profile either here or here at these two places, divided by a uniform velocity, the mean velocity across there. And that has to be integrated over that area, of course, because the velocity v is changing across there. So this is kind of a complicated thing, but it turns out that the application of it for the problems that we need to do is quite simple. And we normally have alpha being equal to 1. So if we look at these situations for For a fully developed turbulent flow in a pipe, alpha is approximately equal to 1. It's also approximately equal to 1 for a nozzle or a converging section, and also in wind tunnels. So we can see that for many different applications, we're able to basically substitute if we go back to the equation, we're basically going to be able to substitute V bar for V, because alpha equals 1. Now, if we get to a more complicated situation, we'll talk about the difference between turbulent and laminar flow later on, but for a fully developed laminar flow, we may need to use alpha equal 2. So, and if we have a special situation, we can always calculate alpha if we know the actual velocity profile. So we can use this equation here to actually calculate what alpha is. And you can look at that. Example 7.1 actually calculates the kinetic energy factor for laminar flow. So that's an example that you can look at in the book. But the bottom line is that this alpha thing, the use of the kinetic energy correction factor turns out to be kind of a convenience for us. And in a lot of cases for the problems that we'll do, alpha will simply be 1, or it will be specified for a particular flow situation. So when we have this equation now, or when we make these simplifications, we can start to look at kind of the final steps of the development of the energy equations. And so what we have now is we have we're going to be integrating over one area and setting that equal to the other, a second area, and this would be an example of that. We've defined a control volume with two control surfaces where we want to know where we either know the information or we want to know the information. Now we've got a pump in here, and so we've got this situation here, and so it's a familiar application of the Reynolds transport theorem. And so we've broken the equation into two different areas of flow. We're going to make some assumptions. Once we assume steady flow, and also assume that things do not depend on temperature, we're able to pull things out of the area integral. And so now we're really starting to look like Bernoulli's equation in the fact that we've got kind of a pressure term, or something that's starting to look like a head term here, an altitude term here, we still have some integrals to deal with, but we'll see in a minute how those simplify out. We're still carrying the internal, the heat transfer terms and the shaft work over here. But remember, these two P's have come from the flow work. Those are the pressure forces, but that's conveniently packed into here. So when we make an additional simplification here, if we can factor out or basically set the density times the velocity integral over area, that really, as we've seen before, is just rho times the mean velocity, the area weighted mean velocity times the area. And that is m dot for the uniform velocity, or the mean velocity. And we can also express this integral as being alpha. This is very key. The math can be shown that we can pull alpha out front, and this v turns into a v bar, and we have alpha times the density times the mean velocity cubed over 2 times the area. So this is really simplifies the equation out now. So it's really starting to look more and more like Bernoulli's. If we divide through by m dot now, we've got m dot here and m dot there, these terms are going to have m dots. So these are now divided by m dot, but these are all now really looking like Bernoulli's equation. If we go one step further, and divide through by gravity, this will now be rho g. That'll turn into a gamma. The g cancels here, and we begin to see some things that look like velocity head, and this equation looks a lot more like Bernoulli's. Now note that we've done some rearranging. We've now separated the shaft work into positive work on the left-hand side being done by the pump on the fluid. So this is now pump work, the rate of work being done by a pump divided by basically something that looks like the force of gravity is basically the rate of gravity. Remember, m dot can be changing. This is the mass per unit time, so this is a little bit different than mg, but this is looking like a gravity term here. We also have a comparable term for the turbine, the work being done by the turbine, the rate of work being done by the turbine. And we note that, remember, the shaft work was turbine minus pump. So we minus that is leaving a positive pump term over here, and we've basically subtracted this over to the other side. So the turbine work is positive on the left-hand side of the equation, and we've lumped this all off over here. And so these terms here are looking much, much like Bernoulli's equation. But we have 1, 2, 3 new terms. And what those turn out to be are, number 1 is the pump head. The pump head is the work per unit time done by the pump on the flow divided by the weight per unit time of the flowing fluid. So that is what the pump head is, and we will learn how to use that in the equations. Number 2 is the turbine head, H sub T, and correspondingly that is the work per unit time done by the flow on the turbine. So this is going to be basically work that's being extracted per unit time out of the fluid, and that is also divided by m dot g, the weight per time of the flowing fluid. And then also we have this new term called the head loss. And what we have done is lumped the internal energies, U, into that term, and as well as the heat transfer, Q dot. So we've got these internal energy terms, the difference in internal energy between the two situations, U2, the two points in the fluid, points 1 and points 2, minus any internal energy or heat transfer into the fluid. So the head loss, as stated in the book, is the conversion of useful mechanical energy. This is our third term here. The head loss is the conversion of useful mechanical energy to waste thermal energy through viscous action. And so it's basically a loss term that's going to extract energy out of the fluid because we don't have a perfect situation. This is analogous to thermal energy that is produced by friction. So in some of the statics and dynamics problems that you've done in the past. Excuse me. So the physical interpretation is that we are looking at the energy balance over control volume, and the energy, the control volume is going to have its own energy, and we're going to have energy into the control volume that can be either put in by the flow itself, energy flowing in the form of kinetic and potential energy, or a change in internal energy for that matter. And we can also add energy via pumps. this is going to equal energy out, and we're going to have energy flowing out of the control volume through a control surface here, but we are also going to have energy losses due to viscous effects in the head loss, and also perhaps we can extract energy out of the flow by putting a turbine in there. So we're back to our summary of the energy equation. We now have an equation that we can work with. It looks awful lot like Bernoulli's principle. We're going to apply it in a very similar way, although we're going to have to obviously deal with the alpha term, the kinetic energy correction factors, which are right here. These are multiplying basically the velocity heads. And we're going to have to remember all these major assumptions that were made in using this equation. So these are going to have to be applicable here in order for us to be able to use this. And additionally, we are going to be able to include energy being pumped into the fluid by a pump, energy being extracted by a turbine, and of course we're going to need to account for any of these viscous losses. To apply this equation, we're going to use a similar situation to what we've done before. We're going to apply these steps. So step one is selection. Make sure you select the continuity equation when the problem involves pumps, turbines, or head loss. Check to ensure that the assumptions used to derive the energy equation are satisfied, and you should be writing them down. So you should be writing the assumptions down. Are the assumptions satisfied? And you should write them down on your problems. The assumptions are steady flow. You can only have one inlet and one outlet port at most. It has to be constant density. So it's going to be much easier to do these problems with liquids than gases. And we're going to have to neglect the thermal energy terms except for those that are associated with the head loss, H sub L. We're going to be needing to select a control volume, and we will label the input port as 0.1 and the outlet port as 0.2. And as usual, locate these sections where you know information and where you want information. By convention, engineers usually do not sketch a control volume when applying the energy equation, but I think that's, I don't understand why that is. I think it's perfectly fine to do this. If it's useful to you. Analysis, write the general form of the energy equation down and conduct a term-by-term analysis, and that would be this equation right here, and you would be going through and seeing what you can eliminate and what you cannot eliminate, and then what's given and what you need to solve for. And remember, you may need to use the continuity equation to fully develop the equation into something that you can solve for a single variable. And then validation. As always in this class, check your units and check the physics. Remember that you've got your pumping head in via the fluid flow and the pump, and you're extracting energy out from the fluid flow, any turbine that you might have, and the head loss. So that is it. There's a couple of examples that you might take a look at for section 7.3. Example 7.2 is one as well that you might take a look at. All right, that's it for section 7.3. Thanks.